Hi everybody, this is Dominic Forbush of Sandia National Laboratories, and today we're going to be talking about modeling oscillating water column type devices within WEC-Sim. Now this is a bit of an unconventional training because we'll actually be encouraging you to break the WEC-Sim library blocks so that you can customize them to meet your own modeling needs. But because of the vast array of different kinds of oscillating water column devices that we've been asked for assistance to model, it's very difficult to propose just a one block solution. So hopefully this more tutorial style format will also be informative. Now recalling the WEC-Sim workflow, the first step of getting a WEC-Sim model is getting a set of boundary element method coefficients suitable for your geometry. Now for an oscillating water column type device, the WEC-Sim team has used three different ways to arrive at these coefficients. Beginning at the far right, perhaps the most intuitive is to treat the internal water column and the surrounding solid body as two separate rigid bodies, wherein the relative motion between them is what is explicitly considered. This is perhaps the most intuitive, as I mentioned, and is something that's available in almost all open source and commercial boundary element method codes. In contrast, you can keep a single body modeling approach, but define the motion of the free surface as a generalized body mode, a flexible mode of the single body. Or within WAMIT in particular, you can define it as a free surface pressure, which changes the solution method boundary condition and is basically a shortcut to the generalized body mode formulation. So here we see a slide summarizing the pros and cons. I won't read through this exhaustively, but just to highlight a couple of things. Though the two rigid body method is really intuitive and it's great with the standard WEC-Sim blocks, the end result is a 12 by 12 system for the minimum of two bodies and 6 degrees of freedom, which can be painful to tune. And this can be really difficult for a floating oscillating water column where the off-diagonal coupled modes between these two bodies are very significant in the dynamics and not that intuitive when you're trying to interpret these boundary element method results. Looking at the other two, although they're not all available in open source methods, you can certainly use the generalized body mode in Capitaine, which is an open source boundary element method solver. If you were to do so in WAMIT, you need to modify a Fortran code and recompile it. Not quite as easy as doing some other things within the WEC-Sim workflow, but definitely possible. The generalized body mode can conceivably define many different surface modes, not just the up and down mode of the free surface relative to the surrounding body, but also sloshing and pitching. Free surface pressure is basically, as I've mentioned, a shortcut method to the generalized body mode that doesn't require you to mess at all with the Fortran code. You just have to specify which panels are your internal free surface. However, both of these methods have the problem that they have some very large undamped responses near the resonant modes of that internal free surface. And we'll get to a way that we can deal with that here in a moment. So as a quick summary of all the available modes, the one that we recommend in general is to use the generalized body mode. This is available in some open source boundary element method codes, so this would be our recommended approach. If you happen to be using WAMIT, free surface pressure should actually be a numerically identical formulation, at least for the heave mode of the internal free surface. We only recommend using the two-body approach if you have a fixed oscillating water column and you can only be concerned with the motion of the internal free surface and not the surrounding geometry. So you may find that even when following the recommended modeling methods, it's very difficult to get good quality boundary element method results for an oscillating water column type device. A number of reasons for that are shown on this slide here. Basically, it's very difficult numerically for a potential flow type solver to resolve all of these issues. I won't talk through all of them, but the one that I would call your attention to is because there is a real physical internal free surface on any oscillating water column type device, that free surface is going to have a resonant mode when the wavelength or multiple integer multiples of the wavelength are of the same length as the draft or the internal diameter of that free surface. And because we're solving this in the context of potential flow, which does not model the vortex losses or any other sort of viscous loss that would be associated with large amplitude motion, the dynamic effect, the predicted responses within potential flow of these resonant modes are going to be very, very significant and dominate the presented dynamics, when in fact, of course, they are non-physical because they'll be subject to significant damping forces in the real world. It's also worth noting that because this is a real physical free surface, the irregular frequency removal tools like those available in WAMET, for instance, don't actually remove these frequencies because those tools are focused on the virtual free surfaces that exist as a consequence of the potential flow solution method. On the right-hand side of the screen, we see some boundary element method results from the generalized body mode method from WAMET of the geometry presented on the previous screen. The internal free surface motion is headed with the heading GBM1 for reference. On the left-hand side, we see a number of characteristics that good BEM runs should have for use with WEC-Sim at least. And we notice that these characteristics don't really fit the boundary element method data, particularly in the degrees of freedom like heave and GBM1 that we care about. These peaks are going to drive the results of the impulse response function, and we're going to have to do something about them if we want to have good quality WEC-Sim runs from this data. Taking a closer look at these peaks, we see that the largest of them corresponds to a wavelength of 0.5 meter, which is the diameter of the internal moon pool. Looking at the peak at a higher frequency, that dimension corresponds to a wavelength of the draft of the internal moon pool. So we can see that these frequencies are based around resonances that are the result of the physical dimensions of the geometry under investigation. The problem with them, of course, is that when we calculate the impulse response function, on which WEC-Sim depends most of the time to calculate WEC dynamics, these frequencies contribute far more than they would in physical reality. In reality, they would be significantly attenuated due to damping at these resonant modes. So as I mentioned, the irregular frequency removal tools like those in WAMET are not likely to be able to remove these non-physical resonances from the boundary element method results because, as we've mentioned, these resonances correspond with the physical dimensions of an actual physical free surface that exists within the device. Instead, we've provided a tool, a bad-bemio fix function, found in the directory in the middle of the screen there, and that follows the method of Kelly et al. Of BEM Rosetta development fame to some extent. I want to emphasize that this function is not a substitute for following best practices of boundary element method modeling. Although it can make bad boundary element method results usable within WEC-Sim, it's absolutely vital that all other best practices are followed for these results to be considered predictive of the performance of your device in simulation. Here we see the results of this boundary element method cleanup code applied to the radiation damping. The raw boundary element method results are shown in the upper right. The cleaned up boundary element method results are shown there at the bottom right of the screen, and the resulting cleaned up impulse response function is shown there at the lower left. And you'll notice that the non-physical resonances of heave and generalized body modes are significantly attenuated in the cleaned up results. And that's vital to arriving at an impulse response function that's representative of the physical response of the device. I want to note that at its core, this post-processing boundary element method cleanup has no knowledge of the real physics of the device. All it's doing is attempting to attenuate what it identifies as these erroneous peaks. This has basis in reality in that these peaks will not actually appear on the physical device because they'll be heavily attenuated by damping, but the actual physics of this damping and this attenuation are not reflected in the boundary element method cleanup code. As a summary of boundary element method analysis of oscillating water column type devices, because of the shortcomings of BEM type analysis in this context, it's really great if we can have any sort of tank testing data or reference model data at all that we can tune our models against in order to have a lot of faith in their results. While we're tuning them, it's not uncommon to see very large damping values need to be applied, particularly to the generalized body mode describing the motion of the free surface, to make the simulation predictive of physical reality. And depending on the success to which the boundary element method data can be cleaned up, it's also not uncommon that we need to vary the damping coefficient that we're applying to the generalized body mode with the frequency of the exciting waves. From here forward, we're going to be getting into the WEC-Sim modeling of these devices. So from here forward, we're assuming that we do have a good boundary element method data set that we can work from in our models. The first way that was suggested by the BEM method on the far right, the two rigid bodies, allows the most intuitive way to put together a WEC-Sim model. Basically, you have two bodies connected by a PTO, preferably an actuated PTO, so that you can describe the coupling force between the internal free surface and the rigid body, represented here as two separate bodies, through this PTO. And this can all be done with the ready-made drag-and-drop WEC-Sim blocks. However, as noted in the boundary element method part of this discussion, we don't generally recommend you model oscillating water columns as multiple rigid bodies. Instead, we recommend the generalized body or the free surface pressure approach, both of which can have an equivalent expression in WEC-Sim using the flexible body block. However, the flexible body block available within the library does not account for any coupling forces between the generalized body mode and the surrounding rigid body. And in this case, that will be very important because it's quite likely that our actuator, our controller, our power harvesting equipment will be dependent upon the relative motion and the coupling forces between this exact mode. So from here forward, we'll be demonstrating how to modify this library block for a particular case that hopefully serves as a useful tutorial that you can then apply to your own oscillating water column models. Here we'll particularly be demonstrating modifications to the WEC-Sim flexible body library block that are suitable to model a piston type oscillating water column where resistance to the internal free surface motion is provided by an orifice that is rigidly affixed to the surrounding rigid body. It's likely that this will be a library block in the near future, but we're going to step through the modification processes here to hopefully advise you to what you might want to do for your own more general oscillating water column. The very first thing we need to do is add a coupling force between the generalized body mode, shown here by the flexible body modes block, and the rigid structure. So we're adding a couple of inputs and outputs where necessary, and we're going to call this coupling force the piston force. Here we are looking inside the flexible body block, and you can see we're continuing our highlighter line, and we're adding in a controller and PTO MATLAB function block where we can define the forces that our orifice is going to exert between the free surface and the rigid body, and we're summing this with an already there damping and stiffness block. Note that in the unmodified version of this library block, those damping and stiffnesses are internal to the generalized body mode and are not coupling forces that are applied between the generalized mode and the rigid body. However, in this case, they might be useful to us, so we're pulling them into that summation. The caveat here is to be very careful with your definition of the signs here of the motion and the force. Make sure that things are all acting in the appropriate direction given the internal and external frames between the rigid and the generalized body modes. So now we have to describe what we're going to put in that controller and PTO block. Here again, we're considering an orifice of a specified area that resists the motion of the free surface by applying a force from the rigid body to which the orifice is affixed. So with that orifice in mind, here we've defined in our MATLAB function a very basic incompressible orifice equation based upon some fundamental fluid mechanics equations that relate the motion of the free surface to the pressure drop across the orifice as a function of orifice area. The only caveat I will give here when you're doing this yourself is to be very careful with your sign convention and make sure that free surface motion in a given direction is exerting a force of the correct sign on the surrounding rigid body. With the piston force output from the flexible modes block all sorted, we'll extend our highlighter line in two directions. Firstly, we'll go down to the flex out to workspace structure, highlighted in red. This will just populate the piston force as an output field in our output structure when the run finishes, so we can keep track of it. And in the other direction, we're going to go to the newly created piston force input of the structure block. And as we step inside here, we're going to recall that our boundary element method's generalized body mode was defined to be the relative motion in heave of the free surface relative to the rigid body around it. So with that in mind, it's appropriate to add this piston force to the third translational force element in this MUX block here, because the heave direction is going to be aligned with the local heave direction of the buoy in its own reference frame. So even as the buoy is excited by the waves and pitches, its nominal heave axis is going to align with that which we've calculated as the output piston force within the flexible body mode. This might look a little different for you if your rigid body mode, or excuse me, if your generalized body modes were defined differently, or it might be more complicated, for instance, if your orifice was positioned at an angle perhaps, so it wasn't just acting along the nominal heave direction. Then you would have to do something a little more complicated here, because the coupling force to the rigid body modes wouldn't just be applied in your heave direction. Here we're showing the output of some multiple case runs that varied orifice area and wave period independently, and plots the normalized power output of power dissipated across the orifice as the surface. We'll see, sort of aligning with physical intuition, that there's kind of a sweet spot of orifice area that depends on the exciting wave period. If your orifice is too large, there's not a significant pressure drop across it, although the flow across it is very large. And if your orifice is too small, the flow across it is also very small, but the pressure drop can be quite large. So what we want to do is balance those two parameters. And because that's sort of what we see here, that gives us confidence that this implementation is capturing the right physical phenomena. This has been Dominic Forbush of Sandia National Laboratories. Thank you for listening to this training about modeling oscillating water column type devices in WEC-Sim. I encourage you to check out our GitHub for other webinars and training materials. And as always, if you have particular questions or issues, go ahead and post to our issues page, which you can reach also through that same GitHub link. Thank you very much. Have a great day.